Hello and welcome everyone. For us, the efficiency in Earth observation deep learning is a dual challenge question. On the one hand, we have the data efficiency, which is the main problem that we have dealt with in the first paper, which is NVDDPM, in which we propose a diffusion data augmentation technique focused on high spatial resolution remote sensing imaging acquired by drone. These kind of datasets are characterized by not only the high spatial resolution, but also by a high cost in the acquisition. This makes that our datasets are quite small, and also we usually have a very hard imbalance among the distinct classes that we have in our dataset. On the other hand, we attach the computational efficiency in the paper called Simpler. In this case, we move from drone dataset to satellite imaging. In this case, the data is much more cheaper, but the characteristics of this data is that the spatial resolution is much slower. We move from 10 centimeters that we have in drone data to 10 meters that we have in satellite. In this case, the Earth observation community could be able to develop foundational models that give us the opportunity to take advantage of this amount of data. As a consequence of that, we have very big models that we have to deal with. And this is the context in which we propose a technique to easily adapt the foundational models to a concrete task, paying attention to the latent space. So, starting with the NVID proposal, from an engineering point of view, what we have is a river basin dataset with reference information. At this point, what we have is a segmentation problem. And we firstly are going to apply a superpixel segmentation, and a patch extraction. With this step, we move from a segmentation problem to a classification one. In this classification problem, what we are going to do is firstly to train a diffusion model, a vision transformer diffusion model. Once it is trained, we could generate synthetic data. In this case, we are going to apply an EBDA control module, which is responsible to generate the exact amount of data for each class to augment our training dataset to train the final classifier that we are going to apply. From a more research point of view, what we have is a dataset that is characterized by this small amount of data, and also the imbalance that we have among the distinct classes. With this data, again, we train the vision transformer that is going to be able to generate synthetic data. We are going to generate synthetic data, but we are going to generate the data with an equilibrium-based data augmentation technique. We are going to combine this real and synthetic data, and with this new combined data, we are going to train a classifier. It's important to highlight that this is not something that improves the precision. This is also a technique that is able to solve some biases due to the prior probability that we have in our real dataset. So, with this in mind, we move to the diffusion intuition. What is the diffusion paradigm? So, we start with a point that represents one sample of our dataset, and we are going to iteratively add more and more noise that belongs to a Gaussian distribution. And it's this Gaussian distribution that gives us the opportunity to assume that when we have time equals to infinite, our data belongs to a Gaussian distribution, which is a distribution that we are able to sample easily. So with this in mind, we could build a diffusion space. Diffusion space that when we are in time equal to 0 is our original distribution dataset. We have some samples. In this case, we are representing our original distribution in a space that is only one-dimensional. In our case, we have a very high dimensional space. Yes? And when we have time equals to infinite, in our case, time equals to 100, we have a pure noise space. So in the middle points, what we are doing is iteratively assign a probability for each element of our space conditioned by the time step. And we are doing this in the forward process. When we are generating, we are starting from random points in the Gaussian space, and we are following the curve that gives us the maximum probability at each time step. So at the end, we start with a pure noise Gaussian sample, and we achieve a point that belongs to the original distribution. Yes? So with this in mind, we have concretely a process that iteratively, the top left part of the slide, assign this probability. This is the training of the model. The right part of the slide represents the forward pass through the curve that is giving us the maximum probability at each time step. So this is the synthesizing stage. Yes? We implement this inverse problem training a numerical function, which is a Vision transformer in our case. To train this, we apply a combination of two different loss functions, which is mean squared error, a very usual loss function for regression problems, and Kalbach-Leiber divergency, which tries to introduce to penalize if the model is not generating diversity in the samples. Yes? With this diffusion model, we are able to generate synthetic data. As you could see, qualitatively, we could see that our data for the vegetation classes and also for the human-aided classes, the generated samples are almost indistinguishable with respect to our real samples. And this is important not only in the fidelity of the samples, but also in the diversity of the samples. Yes? So once we have a model that is able to generate synthetic data, we are going to control this generation. This is the equilibrium-based data augmentation. Basically, the idea is that we are going to generate more synthetic data for the underrepresented classes that we have in our original dataset. With all this stuff, we have these results. You have 5 columns at the left part of the table in which you could see previous GAN approaches. And as you could see, our approach based on diffusion models is not only improving the average accuracy in average across all the datasets in 6 percentage points. It's more important the fact that our approach is agnostic to the classifier, so we can apply different classification strategies, as you could see, a swing transformer, a Vision transformer, or a CNN. And one interesting insight of the results is that, as you could see, even a very small model with only 30,000 parameters could achieve better results than previous approaches based on more than 1 million parameters. This gives us the intuition that our problem is more data-driven than bias-guided. Yes? So with all this in mind, we must to make a step behind, because we have assessed the quality of the generated data from 2 different perspectives. One is the qualitative. We have seen the results as images, and we have applied this technique as data augmentation. But if we want to assess the quality of the generated data, we are going to propose a quantitative approach alternative to these ones. This is the adaptation of other previous approaches used in computer vision. So here, what we are going to do is to take a huge model, which is a ResNet, trained on only one dataset, and we are going to extract the features in the latent space after the backbone. Yes? So we are going to generate points for the real and for the generated data and save the latent space. With this idea, what we have is something like a manifold, an n-dimensional manifold, in which are living somehow our real and generated data. So the first approach that we could do to measure how similar are them is a distance among distributions. So this is the idea of the Fréchet inception distance. We are going to assume that our characteristics, our features, belong to a multivariate Gaussian distribution, and we are going to measure the distance among these distributions. But we can do better. Why? Because the first idea that we can have in mind is try to think if our generated images are similar enough to our real images. So the idea that we are trying to assess is the fidelity. This is done through the precision metric, which tries to think if our generated data are close enough to our real data. And we are assessing how much of our generated data, generated data are close enough to the real data. This is divided between the total amount of generated data. So if we have some samples that are very far away of our real data, these are samples that aren't measured by the precision. So as much we have a high precision, the performance is better of our proposals. Then we can think the other way around, because we can think about if our generated data represents well our real images. So in this case, we are going to measure if all the real samples are close enough to our generated data, divided by the total amount of real samples. With this idea in mind, what we have is that if there are some samples that are present in our real dataset but are far away of our generated samples, this is decreasing our recall measure that keeps this idea, that measures this idea of diversity. With all this stuff, we have the following results. The key element is that we are comparing GAN versus diffusion model, and even when in all the metrics the diffusion model performs better, the big improvement in terms of performance is in the recall, is in the diversity of the generated data. Then we now move from drawn and high resolution and small amount of data to simpler, which is focused on satellite data, a lot of data, and foundational model. And here the target of our approach is try to reduce the computational cost. So we are going to propose a technique to easily adapt our foundational model to our target dataset. So here we have a standard structured pruning pipeline, firstly. So usually we start with a full fine-tuning of the whole foundational model. Once it is fine-tuned, we are going to pay attention to the weights, to attend to the model that we are going to prune, and the user must to indicate how much prune he or she wants to apply. So the users must to introduce this parameter. Once we have the model pruned, we need to do a new fine-tuning of the final model, the pruned model. In contrast, our approach is different. We think about the model not only in terms of the model itself, but also in the context of our target data. So to do that, what we are going to do is take the foundational model, pass through the model in a forward pass some samples that correctly represent our target dataset, which in this case are 500 samples, and we are going to store the latent space. As previously, we are doing something similar to the previous matrices. Once we have this latent space stored, we can calculate a similarity measure across all the latent spaces that we have in the model. And we are going to propose an optimization problem that gives us an optimal cutoff of our model. Finally, we are going to do a fine-tuning of this last small model. This is important to highlight that we are keeping only the less expensive computationally model, and we are removing the most difficult step of a standard pruning pipeline. So the idea is that for us, a foundational model is nothing more than a composition of numerical functions. So what we are going to do is to interpret this in this sense. So we have a domain, which is the input of our model, and a codomain, which is the output of our model. So we are going not only to pay attention to the function itself, but also we are going to pay attention to how are these functions moving the points in the latent space, so in the domain that we are using. So with this strategy, we are extracting the latent spaces, and we are going to measure the similarity among all the latent spaces. So we collect some latent spaces that represent the whole dataset, and we are going to calculate a similarity metric. The similarity metric has to fulfill some mathematical properties, and with all this stuff, we are going to build a matrix heat map that represents the similarity. As you can see, this matrix heat map has a diagonal which has the maximum similarity of the representations, because it represents the similarity of one layer with itself. And also, this matrix has a symmetry with respect to its diagonal, as you could see. And it's important to highlight that there is a behavior not only detected by us, but also by other researchers, that detects that in the early layers there is a very high change in the representation of the latent space for the samples, and in the depth layers there is an stabilization, which means that the representations for these points suffers a very little amount of change. So with this idea in mind, what we are going to do is propose the optimization problem, which we are going to build two submatrices, the early layers and the depth layers. The early layers tries to improve the divergency among the distinct elements of this matrix interpreted as vectors, and the depth layers that tries to improve the similarity among these layers. So with this idea in mind, what we are going to do is calculate all the possible cutoff points and select and use the optimal one for our problem. Well, moving to the assessment of this approach, for us is important not only to take into account one perspective, the training efficiency or the inference efficiency, because pruning is focused only on the inference efficiency, on LoRa or other BFT techniques like layer drop improve only in training efficiency. So our approach is a dual challenge. We try to keep as much performance as we can. In this case, we are dealing with a weak segmentation problem, which is measured, as you could see, as a mean intersection over the union. And at the same time, we try to improve training and inference. And we compare our approach with pruning, with LoRa, and with other techniques like layer drop. An important element to highlight here is that our approach is orthogonal to other PFT techniques like LoRa. As you could see, we can combine our approach with LoRa, and we have also in the paper compared our approach with layer drop, for example. Then, to conclude, for us, the efficiency in remote sensing is a dual challenge. In these cases, we have two extremes of a real line, in which we have very scarce data or very high amount of data and foundational models. But some of the real applications that we have in a satellite to detect disasters or other situations, the reality is in a middle point of these two scenarios. From a data-centric point of view, it's important to highlight that moreover to the amount of data, is very important the imbalance among the distinct classes. And from a model-centric point of view, what we noted is that the foundational models that we have in Earth observation, we apply 5 different foundational models. The behavior that we could see is that exists an stabilization, and this stabilization is dependent on the data. So we achieve very different cutoff points. Finally, as a unifying conclusion, the systems that we are going to build with these strategies must be guided from the beginning with these two ideas in mind, with the data scarcity aspect and also the computational cost in mind. And this is all. Thank you.
All right. Thank you very much, Víctor. If not, I can start with a couple of questions, maybe to make you, start later on. Yeah, well, the first question is, so now you are in what stage in your thesis? Because I saw that you had 2 papers, right?
Well, one is a preprint. The simpler is in a preprint. Yes, it's submitted, but we are waiting for the reviews.
All right. So the first question is about, I've noticed that you compared your diffusion model with GAN models. Okay. Hola. Let's go. Hola. Hola. Sí. Okay. All right. So the question is, I've noticed that you compared your diffusion model with some other GAN models. Is there any approach in the literature using diffusion models for you to compare with? Because you compared your model with GAN models, which lag, let's say, behind diffusion models in generative AI, let's say. So my question is, if there are some other diffusion models related to your topic of research, and if you compare them with your model, let's say.
At the point that we have submitted this work to the journal, we haven't found out any other diffusion data augmentation technique with real results. There were some data augmentation techniques, but they aren't focused on the generation, on the pure generation. So this is one of the problems that we have in order to compare to other situations, and also we are usually working on this high resolution, spatial resolution data, which is very complicated to find out other data sets that could give us a fair comparison, because the biggest part of the Earth observation community is focused on this second part of data, the satellite data. So the reality of the behavior of the models is very different when we have very high spatial resolution and when we have low spatial resolution.
Yeah, I understand. I understand. Yeah, another question, genuine question, is about the Frechet index. Does it work?
Sorry?
Does it work, the Frechet? The Frechet metrics to compare,
Yes, yes.
let's say, real and synthetic data. I mean, because I might, it might be the case that I took it wrong, but the Frechet index, or maybe I took it wrong, I don't know. But so in the end, to make sure that your synthetic data are good enough,
Mhm.
do you rely on Frechet index or on the accuracy? How do you do it? Maybe I didn't get it.
In the paper, we have done the quantitative approach of the generative metrics at the end. So we have selected the foundational model and trained, the diffusion model, and trained the diffusion model without taking into account these metrics. This is
The Frechet index.
No, well, it's Frechet inception distance.
Sorry?
Frechet inception distance.
Okay, so so my question was if the latent space was, let's say, a reliable representation for you to compare
Yes,
both through the Frechet index.
Yes, one of the contributions that we have done in this paper is build a huge model that accurately be able to represent the distinct amount of data. So to do that, we must to make a special configuration of the training of this huge model.
Okay.
Because usually due to the imbalance among the distinct classes, the question is that features that are more relevant for classes that are big are more represented in a usual huge model. So to solve this, we have to train a model that was trained in the same amount of data for all the classes.
Yeah, I more or less get it. Thank you. Questions? I mean, anybody? Does anybody to make a question or a comment or anything? No? If not, let's thank to this marvelous speaker again. Nice presentation.